Our next talk is going to be by Afra. She is an assistant professor at the University of Washington, and I've actually known Afra for a long time. We were colleagues back in Bell Labs. So she was a brilliant colleague then, and she's turned into a brilliant professor now, and now she's decided to do more federated learning work. And so I'm really happy to see what she is doing these days. Afra, can you hear us?
Yes, hi everyone. I can hear you. Yeah.
And we can see your slides. So that's good.
Thank you, Nick. So I just get started. Okay, hi everybody. My name is Afra Mashhadi. I lead the Computational Behavior and Modeling Lab at University of Washington. And the work I'm presenting today is on deep embedded clustering for federated learning. And this is a collaboration with past students, future students, but majority of the work is done by Afra Mashhadi, who is already graduated from my lab. So let's just take a quick look at the outline of our presentation today. I'm going to talk a little bit about the motivation behind this work, and I'm going to present a little bit information about what is deep embedded clustering, what are the methodology behind it. Then I would present a use case on how we can use deep embedded clustering in federated learning. And then I will show some limitation of our work and the future works, and if there's any interest in collaboration with our lab. So let's look at the motivation. You have so far have heard lots of great work, given that this is like probably in the evening time, at night in the UK time. So you have seen a lot of different type of works that can be done with machine learning, and especially in the distributed learning and federated learning. One of the challenges that my research lab focuses on is on the real world challenges where we don't have labels associated with the data that we are collecting from the people. So the previous talk was actually a great example of that, where you have the data from the mobile devices and you do not necessarily have a specific ground truth labels with them. So when we talk about the label scarcity, it can happen because of two different possibilities. One is that a lot of times labels associated with the data, it requires domain expertise. For example, in the context of health, in the case study that I would show with the heartbeat diseases, you need to have a medical doctor to actually diagnose those. And other cases, it's just labels are really difficult to define, especially in terms of the socio-technical problems, such as looking at, for example, urban communities. How do you define a label for data that comes from mobility data sets, right? So this is why we are concentrating on majority of our work of our lab is on unsupervised learning. And deep embedded clustering is a type of unsupervised learning. Put it simply, you can think about merging representation learning together with the clustering to train a model simultaneously. So let's dive in. Let's talk about the first component, which is the representation learning. So with the representation learning, you have a unsupervised neural network, which aims to generate the output, which is as close enough to the input that is read by the network. So you can think about the input being images or audio data going through various layers, and specifically reducing the dimensionality of that data to a code here, whatever we call a code, and then trying to reconstruct it back such that it has a minimum differences between the output and the input. So there are no required labels associated with this. Oops. And a well-known type of representation learning is actually autoencoders. So here is an example of autoencoder that has convolutional layers. So you can imagine that an image passes through these convolutional layers. And the top branch of this model, we would try to reduce the reconstruction loss. So we want the model, after the features are extracted, we want to be able to reconstruct it such that we minimize the reconstruction loss as formalized here. And so you can think about in the example of when your model is basically based on images and convolutional layers, you want to have the top layer is the top images are the input that is gone, and the bottom is the reconstructed output. So you want these to be close enough to each other. So what makes the deep embedded clustering different from the autoencoder is actually the fact that we have this lower branch down here. And when we are training the model, we're going to train to reduce two sets of losses, not only the top part, which is the reconstruction loss, but we try to actually reduce the clustering loss as well, which is based on reducing the KL divergence between the two distribution of P and Q. And here, the distribution of the P is the target distribution, which is calculated based on the similarity of the embedded points and the cluster centers mean here. So for more information on this, you can refer to the technical papers behind this work. So when we put them together, our objective is to reduce this loss as overall loss. And obviously, one important question comes up on how do you weigh them? Do we want to, prioritize the weight of the reconstruction loss or the clustering loss? And this is actually an important, very difficult question to do, especially in the federated learning setting. So you can see that if, for example, gamma is set to 0 in here, we would have just the autoencoder network, which would just try to reduce the reconstruction loss. If we set gamma really high, we run into risk of actually distorting whatever we are learning. So reducing the reconstruction loss weight would become also it would give us a worse result. So there is a balance between the learning rate and this setting these hyperparameters. So let's look at it, how we're going to actually apply this in our work. So how can we, what can we use it for the deep embedded clustering? One of those use cases is heartbeat biomarkers. So we can think about the listening to the internal sounds of the body. These days we have varieties of devices that can monitor the heartbeat sound, and there's a lot of research done in terms of machine learning on the heartbeat detections and diagnosis diseases, but majority of them have worked on the centralized machine learning setting, and they usually use the clinical studies where the patient's being monitored in the hospital, the heartbeat sounds are collected, and then the classification happens afterwards. So our idea is to address some of these real world challenges by looking at variety of devices, so not only hospital devices and professional equipment, but also looking at digital stethoscope, that's the picture on the left, looking at the iPhone attached with a stethoscope, or just iPhone by itself, recording the heartbeat sound, and then also maybe future work of looking at earables and so on. So our work would actually open up a possibility for actually collecting the data and training it on a non-clinical setting. So when patients are at home and on their own environment. And if we are able to actually do it on a federated learning, we can also reduce the privacy concerns of data being shared across out of the patient's devices. And also we would be able to run it on a mobile device, the training of the model. So I'm not going to go through these heart sounds because of the interest of time, but I'm just going to say that you all have a heart, so you know how your heartbeat sounds like. When it's normal, you have this lobbed up effect where you have these things you can see on the spectrum here. For any other kind of heart sounds, which is not normal, you would observe that there is some sort of a sound in the middle. So here you have a murmur heartbeat sound, which there's a whoosh here in the middle, and different type of diseases would have different associated problems in the middle of the lobbed up sound. So for our study, we actually just collapse everything that is not normal into an abnormal sound, because we are just interested to train the model to learn what is normal and what is abnormal. We have two sets of data sets which are openly available. One is Pascal, which is collected through iPhone app and a digital stethoscope, so 2 sets of devices, dataset A and dataset B. And we have another dataset, which is a PhysioNet, and this is a professional stethoscope from hospital recording. And you can see in here the differences in the terms of the number of sound files that we have. The Pascal dataset is very small in terms of the number of files that we have. PhysioNet is a much larger dataset. So let's look at our overall architecture of our work. We have an app that collects sound, even though we haven't actually done any kind of a data collection ourselves, and we've been using the data sources outside of that are publicly available. We then have a pre-processing stage where we go through, we pass the sound through a low pass band and we downsample it. We make sure that all the clips are the same length, and that's what is required for our model to have the same length clips. And then we extract the features using MEL spectrograph. So going through this just very briefly, we need to remove some of the background noises. So we trim the beginning and the end of each sample, because when the microphone moves near the clothes, it's very noisy. And we don't sample to a specific sampling rate. And again, I'm not going to go into details of this MFCC, but we pass our input through the MEL frequency, and we actually, the output of this pre-processing is what goes into our model. So let's take a look at the model. The model is, again, the same thing as I discussed, is a deep embedded clustering, but in this case, our layers or LSTM layers, given that we are handling audio sound. We have a few dropout layers and a dense layer. So the input, when it's going through the LSTM layers, we have an encoded layer here, which is the length representation of that sound. And then the 2 branches of the clustering, reducing the clustering loss and reducing the reconstruction loss. And again, we have these 2 parameters of gamma and gamma prime, which we play with and tune. So let's look at our results in terms of a benchmark comparison first. So here's our, when we look at the centralized setting, so there haven't been many work that have done a federated learning of this heartbeat diagnosis. So our comparison is limited to the centralized settings, but there have been a lot of work that have done different types of centralized studies. So here we can see our approach is very much comparable in terms of accuracy. He et al. Uses segmentation, which requires a lot of pre-processing, and that's why we do not do segmentation. That is detecting where the heart beats, the lob dobs are first, and then processing it. And because we want to do this on the mobile devices, we do not do any segmentation. Raza et al. Does also better in terms of the accuracy than our model, but they use 782 features to train. And our model is very light, so it's only 40 features. And we have also done measurements on how long it takes on the devices to perform. So let's look at our federated results. Here we have the results for different gamma, setting gamma differently, so giving more priority to the more weight and the priority to the clustering objective. And for a different number of clients that were on the device farm, Amazon device farm. So we can see that each client has how many recording. Here in the parentheses is a number of recording. Each recording is 5 seconds. So these are very short periods of heartbeat recording. And we can see that our approach actually is very good in terms of identifying accuracy and NMI and ARI, which are the commonly way of measuring the clustering purity and efficiency. With the Pascal dataset, actually, given that the files are not as much, we don't have that many recording from this dataset. You can see that when we increase the number of the participants to 20, then we have only like 20 recording per each participants, but still we do. So this causes a very low NMI, and we have observed quite a low ARI and NMI in this data set. But overall, our work shows the possibility of actually training these cross devices using federated learning platform, using the Flower platform to actually train these types of model on the devices. So some future work includes multi-device sensing. So we currently kind of have that because we have devices from Pascal or from different type of devices, but we are working with cardiologists at Europe Medical Center and other collaborators in University of Washington to actually expand our data set. Our study actually lacks comparison with other federated learning clustering baselines, and that's something that we see to be very much vital to do a comparison with. And if you're interested in doing so and working with us in baselining this, we would be happy to collaborate with you. Another thing is that our study is not focused on the socio-technical challenges of these topics. So whether there are any ethical issues or any acceptance issues from people to actually, participate in this type of training. So we are just focusing on the technical side of this work. Finally, before I finish for the questions, I just wanted to say that here, this was a very short talk, so I didn't want to go to our second use case, which is on the urban community detection, but you can apply the same methodology of deep embedded clustering to actually detect the urban communities. So if you're interested in this, take a look at our paper from last year or take a look at my website for more current work that are going on. So I want to say a special thanks to the Flower community. For the past year, my students have been collaborating with them, and really a great thank you to them for the great platform and also being very open to questions from us. And if you're interested in collaborating with me, we are always open to having enthusiastic people to work with us. So drop me an email, and thank you very much. And if there's any questions, I'm happy to answer.
Thanks, Afra. That was a great talk. I know you have to go soon, so we can ask a few questions until that might occur. Questions from the audience. So the question is it possible to use some of the methods you've developed in this work for other types of tasks, an example of which would be segmentation?
Oh, okay. Is it possible to apply this for the segmentation? I'm not so sure actually about the segmentation. So we haven't really looked at that at all. That's something that requires quite a lot of pre-processing, and we didn't want to make our model like heavier because like at the moment we have only, our model takes 30 seconds for pre-processing, and that's what we wanted to keep in terms of measurements on devices. In terms of the methodology itself, I think deep embedded clustering, obviously you can apply it to any, I would say, many different type of problems. So anything that you do not have a label with, but you do have quite a lot of data, so representation can be learned at the same time as forcing it into the clusters, it could be possible. We have applied our method into, for example, detecting sound of whales and orcas from ocean, from sensors embedded into the ocean and the coast of Oregon. And we know that, for example, even for those type of audio sounds, it's very good in detecting this type of biomarine sounds. Yeah.
I see. Any other questions? Yes, one from Daniel.
Which framework or tool did you choose for unsupervised training for?
Oh, I see. So the question was, which toolkit or framework or piece of software did you use for the on-device training element of this?
Yes, very good question. I cannot see you, but I can see you. Very good question. Okay, so we use TensorFlow for the whole thing. So our whole implementation of Flower is based on TensorFlow. But before TensorFlow Lite, so basically for the device part here and what we've done in the Amazon device farm, we had a wrapper around our code, which could then run any kind of a Python code on the Android device. that itself is not a very good kind of a design, but again, this was before TensorFlow Lite could be doing like training on the devices. So yeah, we just use a wrapper that could enable TensorFlow to run on any Android.
I see. Interesting. Cool. Well, well, thank you again for coming, and pleasure. It's great to see your work. Thank you.
Thank you very much. Thank you.